No. You guys doing okay? No? What's going on?
Busy.
Really? Who knew? Calculus and college business, it's crazy. Yay! So, let me ask you a couple things. If you're behind in homework, who should you talk to?
Talk to you.
To me, I made the freaking homework. Can't I change it? It's mine, I made it. I could change it for you. That's one thing I could do. Does it make sense? What do I mean? I could say, do every other problem. Turn that in. I'm not going to give you full credit, but I'm going to give you a plan to get back caught up, right? Now, just to help you, like I helped somebody else out earlier, if you're currently in like section 5.1, drop that shit, right? Do some of 5.3, do some of 5.5, because those are the most immediately important things, right? So like, for example, if somebody right now didn't know how to do derivatives, you think I would tell them to start with the limit definition of derivative? Probably not, because what's immediately important is just being able to do them, yes? Now, does that mean that the limit definition isn't worth shit? No. It just means, holy shit, gotta know how to do derivatives, obviously, right? So if right now you haven't gotten a lot of practice, just straight up integrating stuff, that is your immediate thing. Forget about the sum of the I business, all that kind of stuff. Do 5.3, the F-talk stuff. 5.5, the U sub stuff, right? Does that make sense? Yes?
Where should we be right now as far as homework goes? Like, what kind of?
You should be getting into section 6.1.
Okay.
Yeah. In a perfect world, right? And I, believe me, I think I've told you that as a student, I was never in that perfect world. Yes? Yes? So, I mean, I was constantly behind in homework, and I was constantly turning in incomplete homework, right? And I was accepting my teacher saying, "What the shit, Jeff?" But I lived in my reality, which is all I could do. That sounds kind of woo-woo, but I don't care. Right? So you gotta accept the reality you're in, but you also have to accept the fact that part of your reality is you're in a calculus class. And how do you pass any math class? Practice. Right? I know. I see some eyes rolling, but these are all things we know, and these are all things we as humans don't do for some reason. We don't do what's gonna help us out the most. Okay. So if you are, like I said, if you're back in chapter 5, 5.3, 5.5, focus on those. If you want to come see me and get more specific modifications because you don't want to skip too much, okay, I can do that. Right? Okay. Anything from homework or any other general questions or? No? All right. So what is so let me see. Okay, let's see if I can get something from you guys. How do you feel about just integration by itself, right? Like definite integrals. So let's do a couple examples. Because again, the less you know how to do this, if you don't know how to do an integral, there's no way in hell you're going to do chapter 6. This is what it's built on. So it's got to build up a little bit. So like, all right, just take a minute. I'm going to start off like silly nice. Just do this in for me. Call me over if you're not sure what's going on. right now, that problem should be like a gimme problem. It needs to be. If it isn't, don't feel demoralized. Just go, okay, I'm not where I'm supposed to be. I gotta work on this, right? But just to let you know, where should you be with understanding stuff? That should be easy shit. It needs to be. And again, if that's not where you are, I'm not saying anything bad about you at all. Just not that's where you're supposed to be. And if you're not, oh, okay, shit, I better get there, right? So who can tell me, what's the first step on this?
Is it pi by 1 and then divided by
Yeah, because we discovered, because what is this really asking directly? Let me make sure you guys understand concepts too. What is this asking me directly? What does that symbol actually mean, fundamentally?
Next derivative?
No, it doesn't. We connected it to that, but what does it mean by itself? Area. I love it. Derivative means slope. Integral, antiderivative means area. I like it. And they can be more specific, area between the x-axis or the y-axis, blah, blah, blah. But area is the quick answer. So it specifically wants the area between the x-axis and x squared from 1 to 3. So if we did a little rough sketch, shoot it, 1, 3, it wants this area. Okay. So you can always take an integral back to be the area of something. It could mean something more than that or something, but once you set an integral up, it means the area from this to this under this space. 5.2 and 5.3, I think especially, connected areas with antiderivatives, right? And we did antiderivatives back in 4.9. The minute you know how to take derivatives, you should be able to stop and think backwards to do antiderivatives, right? And which is why I made a big deal out of, if you don't understand derivatives, you're going to suck at everything else in the rest of the class. Because the rest of the class is undoing derivatives, yes? Okay, I like it. So, calculation-wise, I am going to do the antiderivative and evaluate it between these two, but we had to prove that, f top 1, f top 2, we had to prove that those are connected. So what is the antiderivative of this?
X cubed over 3.
Yeah, the power becomes 3, and then I multiply by the reciprocal. Now, do I have to put a plus c on this one? No, because I know it's going to drop off eventually, so it's just convention not to write it. And I'm going to evaluate it from 1 to 3. And then I just throw that shit in, right? So I get 27 over 3 is 9 minus 1/3. So again, it's f of b minus f of a. In this case, this is big XF. So this whole process, you should just be able to eat up. Right? The stuff I put in here is going to get grosser and grosser and grosser, but the actual idea doesn't change. It doesn't change. Okay. So right now you have to honestly evaluate yourself. Do you feel okay with that? Right? And if you don't, you need to put some freaking time in. And I'm not saying you haven't been. I'm just saying focus your time on this right now. Because this is what everything we're doing is being based on. The next level above, I can put grosser stuff in there, who cares? What's kind of like the next true level of this would be section 5.5, U sub, right? So what if I had this problem? Did we finish that one? Not really. What's this? 26 over 3. So, what if I had, let me see, I'm not going to try to make this perfect. Let me put something in here first here. Blah, 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 blah. I'll be really nice. There you go. Can you do it, Jeff? No. Can you? Sure, Jeff. Just do something. That might work, yeah. And again, I really want you guys to understand this. If I have a product and I go to do a derivative, can I just take the derivative of each piece and just be done with it? Like if I had x times sine x, is that derivative 1 times cosine x, and I'm done. Yay! Right? If I had x times sine x, can I just take derivative of x times the derivative of sine? I'm done. Is that how it works? Anybody? So if I had x sine x, and I want you to take the derivative, can I just do derivative of x is 1, derivative of sine is cosine? Yay!
No.
Hell no, good, good, I like that. Some of you guys are like, shit no, man, what's wrong with you? What about the use? Product, right? Okay. And I've said this before, but I really want you to get this. If derivatives can't handle products well, integrals definitely can't handle product. Holy shit, because they're undoing derivation. Holy shit. There's no product rule for integrals. There's no reason there should be. If derivatives have a problem with something, integrals have a bigger problem. They almost always will be harder because I'm going backwards. Does that make sense? So don't allow yourself to just integrate that, integrate, I mean, right? No way. You can't even integrate this, so you would die a meal. Is this harder than that? Yes, it is, yes? Doesn't it have a lot more shit inside? What method do I need to use for this? Can anyone see what method I have to use for this? You sub. I like it. I mean, real quick, imagine this. How would I do the derivative of natural log of x squared? Wouldn't the 2 come down? Times the inside to the first power times 1 over x. Doesn't that sort of look like that? Right? A little bit? Okay, so maybe that's where that comes from. So what am I going to let u equal here? How can I tell I got this problem? Because we can't, I don't know. But do I see a function in here whose derivative is also in here? Yes. Which function has its derivative in there also?
Well, natural.
Natural log. So if I let u equal the natural log, what's du?
1 over x
So I really want this to make sense. Doesn't this say the integral of a function squared times that function's derivative? Isn't that what that says? Right? That function squared times its derivative. Yes? All this is doing is putting that in our face and saying, okay, that's nice. Write it down. Right? That's how it sounds. Right? It's the voice of math. Hello, math. So I've got to take care of these. I'll do that in a minute. Because these are what does. These, I love that question. These are what does. What's doing this? What's going from e to e cubed? What's the variable in this? What's the variable? X. So that tells you what axis you're traveling along. The x's go from e to e cubed. That's what that says. And what am I about to do? Well, in place of this, what am I going to put? U. So I got u squared. That's what it, right? And then what's this? Du. So I can't put e and e cubed here because that's what x is doing. Now I need to know what the shit u is doing. Right? What is u doing? I always want somebody to walk by. Oh boy, some math people. Got to take an English class. Okay, let me stop for a minute. You gotta let me know. I'm not saying this is easy. I'm not saying this is intuitive. I'm trying to show you. How do you know you've got to do this? How do you know this is going to work? Well, I see a function whose derivative is in there. So I know u sub should work. And remember what I said. Isn't this the integral of a function squared times the derivative of that function? Isn't that what that says? So isn't this the integral of a function squared times the derivative of the function? Isn't that the same thing? They're the same thing. What's it going from to, though? How do I figure it out? I know this, right? What does this mean? That is what is.
X is.
That's what x is, right? X starts at e. So if x starts at e, what does u start at? Right? X is e, right? What does u start at? 1. And what does it end at when x is e cubed?
3.
Use 3. Look what Jeff did. Look what Jeff did. Look what Jeff did. It's the same stupid thing, right? So what that really, okay, this is a little weird. But isn't it possible that this area is the same as this area? If I drew them perfect, it looks like this should be a little bigger. I don't know. Isn't it possible these areas are the same? Are they the same shape? Couldn't their areas be the same? So whatever this function looks like, the area from here to here under that is the same as the area under this from there to there. I just took the shape they gave me and said, that's gross. I just hammered it. There you go. Now it's a better shape. Now I can see what the shit's going on. That's what U sub graphically does. It just changes the shape. Gross shape, beautiful shape. Sorry, don't mean nothing bad. You're beautiful in your own way. Love you guys. You're all like, oh my god, this guy's talking to his phone. And then this we already did. It would all be all the same steps, right? 26. Yes.
So just quick clarification. So what did you do to get the bounds again, the 1 and 3?
Okay. Isn't this what x is?
Yeah.
Isn't this supposed to be what u starts at and what u goes to?
Yeah.
What is u in terms of x?
Use natural.
So if x starts at e, u starts at 1. Yeah, so that's all you gotta do is plug in what x is doing, the limits. Plug it into whatever you call it u, because that's what u is. Oh, sweet, connections. So really, listen guys, I feel like you guys should all get a shirt saying, I survived Jeff's calculus class. Hopefully you all do. But if one of you has a question, there's at least 2 or 3 more that have the same question. You have to always keep that in mind. So these are the kind of questions you can ask. You can go, I really don't freaking understand U sub at all. Okay, let's do, because this just helped a lot of people out. Yes, hopefully. Did it help anybody enough? You guys like, all the shit you say just sounds like, okay, hopefully not. Maybe. The beautiful thing I need you to realize, we've seen, as a student, it's difficult to remember what we've been through sometimes. You just know you've been through a lot. But we saw how this connected to area. Therefore, you can talk about these things in terms of area, and it's beautiful. The area of this thing, it's a different shape. That's a totally different shape than this. But because of what we did, we smushed it, and the area of this is the same as the area of that. Sort of like, did I do the thing with the circle, and we did this, remember this? Remember this? And then I opened it up, and I made a rectangle out of it. See if I remember how I did it. All right, we do the same thing at the bottom. Open it, bam! We smushed it into a rectangle, and I went, oh, I know that shit. You remember that? It's really all we're doing here is just less stuff you can do with paper, but it's the same idea. Okay. So, if you have not done 5.3 and you have not done 5.5, those are your immediate concerns. The other sections are important, but right now, forget about those. And the minute you're done with 5.5, go right to 6.1. Continue forgetting about the other ones for a bit. Do them as you can. Right now, you need to be able to do this for damn sure, and this you have to be able to kind of attack it. Okay. Does anyone want to do another U sub? Or how you guys feel? I'm opening it up. You want to do another U sub?
I have a question. So you replace the U values right at the end? There.
Oh yeah, I'm sorry. So I kind of
It's the
skipped.
same.
Yeah. So this would be 1/3 U cubed. Is that cool?
Yes.
And then I go 1 to 3, but I basically already did the work there, right?
But we never go back to like if there was something else called U, then we would replace it for natural American. Or,
Say it one more time.
you know how you
I don't have to go back.
Something else.
I don't have to go back.
Okay.
So I remember I showed you that alternate way to do this? Where I put the little parentheses and I kept these and I took it back next. The reason I used to teach that way is because what's different about this question here? Is there anything different about this question?
It's impacted.
There's no limits. There's no limits of integration, right? So what's going to be different?
You have to put plus C at the end.
You got to put plus C at the end, right? And does everybody agree all the same steps? Yes. Blah, 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 blah. And I end up here. But is this the answer? You make the threes look like actual threes. There we go. Is that what I'd circle and give to me? Especially me, I'm gonna. There you go, Jeff. Well, thank you, Jeff. That was a weird thing that just happened. Would you circle that and give it to me? Of course you wouldn't. Why not?
Sure.
Because the variable's x. So the u thing in this problem was just something we did in the middle to make the work easier. So the answer here is not going to be a number. It's going to be a function. A function of what? A function of frickin' x, because that's what the variable was that was given to me, right? So this would be 1/3 natural log of x cubed. Here, does some of you guys see why now the teaching I liked doing this where I made them go back to x because you have to go back to x if there's no limits. At the same time, it's a little extra work that's not really necessary as long as you change these. So why do I not have to go back to x? Because the answer is going to be a number, and the number that would be the answer to this is the same number that would be the answer to this, because they're the same area. So I don't have to go back to x. I could. I get the same freaking answer if I did. Okay. So real quick, what if I went back to x? What would I put here? ln x. Cubed. And I would go from e to e cubed. Is that cool? But do you see how that, if I put an e cubed in, natural log of e cubed is 3. So I'd still get 3 cubed divided, do you see what I'm saying? Because this step here, changing the u, the x to u, it captures what it would be if you did go back to the x's and plug shit in there instead. It kind of does that step for you in the middle. Okay? So I know this is confusing, but it's either I teach that you go back to x all the damn time, which means there's extra work here, or I try to get you to understand you only have to go back to x if your answer is going to be a function. This has got to be a function of the correct variable. Here's a frickin' number. Who cares if it came from this shape or that shape? Right? Maybe this is this shape, and this is this shape. Same area, who cares? I don't have to push this back into a circle before I answer the question. Is that me? I know it's weird. I know. Okay. So let me ask you again. You want to do one more U sub? Yes? One more U sub? Okay. And then we'll get into some new stuff. Do you guys have I made you feel like if you ask questions, you're slowing me down or something? Do you feel that way, or you know it's okay to ask questions? It's up to, my job is to accept questions, and if there's too many, I'll say, see me after class. That's my job. It's part of my job. It's not my only. Okay. So, all right, Jeff, make up another one. All right, let's see. All right, let's do 2 more real quick. Let's do a nice straightforward one. You like what I call straightforward? Can you identify why this is not that bad? Why would U sub work? Can somebody tell me pretty quickly or somebody shortly why U sub would work?
There's a derivative for the answer.
Yeah, the derivative of x cubed is basically x squared. Now there's some constants attached, correct? But why do we not care about constants so much? Just to see if it'll work. What can we do to always make a constant show up if I want to? If I need a 7 inside, I just put a 1 7 outside, because numbers can go inside and outside of intervals. So the constant doesn't matter worth shit. But if I see an x to the 7th powers in something, I need to see an x to the 6th power outside somewhere. And then I know u sub should work. Yes, maybe? Okay. So it's a really good first step. How do I tell if u sub will even work? So what am I going to let u equal? 4 minus 2x cubed, I like it. And then what's du?
6x squared dx.
I don't know if you said
Negative.
negative 6x squared dx. I like it. Now, other teachers teach this a little differently. And they're wrong, just to be blunt. All right? Because other teachers teach you to solve for dx, and again, that leads to so many problems. Now, that's my opinion, I guess. I mean, but still. I'd much rather you say, what am I missing? And then I can force it to be there, right? So what do I see? What parts do I see to make du? I definitely see dx, right? What else do I see? I see x squared. So of course I just need a negative 6. So if you throw a negative 6 here, what do you have to put here?
Negative 1 6.
So overall, we didn't change the number. We didn't change this interval at all. Right? But we did reorganize the inside, so it's doable. So what can I replace this with? And let's see, Jeff. Let's learn from past mistakes. There you go, buddy. Look at you go. Yeah, this is du. Bam! This is what's going to happen? Look, 0. What do I put here? You. Thank you. You're like, how long can I make you do that? Okay. And this is something else I wanted to point out earlier. The secant squared is kind of like the heart of this integral. You see that? And the other things are like the extraneous parts of the heart. Heart is secant squared. Can you integrate secant squared? Yes, right? That's an easy derivative. Where did it come from? Where did it come from? Secant squared came from what when I took a derivative of? Tangent. Cool. And then the last step is?
Like the variable factor.
Yeah. I can't have u because it's all x's. So I can think really quickly. Derivative tangent secant squared. Shit, right? Times derivative of this inside would be negative 6x squared. That's negative 1/6 is x squared. Yeah, right? So I do get back to where I started. So that's a quick little check I could do. Derivatives are much quicker than intervals. So you can check pretty quickly. Maybe, is that? All right, one more, and then we'll do a little bit of the next section. That thing is recording, right? Thank you. So let's do one a little bit freakier. Let's make this x cubed. Yeah. I think. No, let's do this. Not make this too crazy. There we go. Okay. Alright, so it should be integral x squared square root of 3x plus 2. So I really want you to understand this. Would I be correct in saying, oh, I see a function x squared whose derivative x is in let me ask you this, is there an x in there? No, there's the square root of that shit in there, right? Maybe. So, if I let u equal x squared, du would be 2x, right? X. I'd have to be able to find an x dx, and I can't, and I have nothing for this guy. So what do I need to let u equal in this case? What do you almost always start u off as?
The inner.
The inside. Let's try that and see where it goes. What's the derivative of this? Second?
3
3?
plus c
No.
on dx.
dx, I like it. So remember, again, the reason we do that is this would have been this before. And we just multiply that up. Because I'm trying to figure out how to make dx become du. So we have a couple problems here, yes? All right, I don't have shit for this guy. It seems, right? I made it really, I like this problem a lot, it's gross. But I mean, here's dx, right? So let's see, all right, integral, I got the square root of u, yes? So I'm gonna put u to the 1/2. I've almost got du, right? What am I missing?
X.
Well, I got a dx, what am I missing? To make du.
Oh, plus 2.
No?
Right?
I need a factor of 3, right? So you gotta think about multiplication. So I'm missing this guy. So if I put a 3 here, what do I have to put outside? 1/3. It's that simple. It's kind of like, okay, I got dx. What am I missing? 3. Oh shit. If I put a 3 there, I better kill it. So what can I replace this with? I can replace it with du. Now what do I still have that I haven't done anything with yet?
X squared.
And if I try to put that there, this doesn't make any sense. So what do I do? Does anybody remember? Do I know something about x? I know something about u, don't I? What's u? That inherently means I know what the shit x is, right? Can't I solve that for x? Remember this? This is the little bit of extra shit on top of substitution that you have to okay. The whole point is to get rid of all my x stuff. So if I knew what x was, I could just put that wherever u is. So what is x? Minus 2 divided by 3. So then right here, I could put u minus 2 over 3 squared. Right, there's x squared. Square root of u d. So all I did, I didn't know what x squared was, but I did have, can't I solve that for x? Of course I can. So now I do know what x is. Bam! But some of you guys, like you're looking at this and saying, that doesn't look much better. Check. See? But let's do a couple things. Watch. What's 3 squared?
9.
Can't I take 9 out? So now I just have this. Is that cool? We can do that immediately. Isn't this stuff divided by 9?
That's how much factor you have to take a 9 out of all the stuff.
You take a 3 out of both, which is a 9. So I just figured 3 squared is 9, that's what it really is. Take it out. So now I just have the stuff on the top left. Okay. And what do I do in here? Can't I FOIL this? And then can't I distribute that? Don't I end up with a bunch of u to a power, which is easy as shit to integrate? Yes. So here. Where's my end? Let's see. What's u squared times u to the 1/2? 5x. That's all right.
I'm sorry.
No worries. So 2 is 4 halves, plus 1/2, 5 halves, minus 4u to the 3 halves, plus 4u to the 1/2, go away. Now, that's sort of ugly, but at the same time, in terms of derivatives and antiderivatives, that's easy as shit. It needs to be, right? Any function to a number power. Easy. So how do I integrate u to the 5 halves? What's the new power going to be? It's 5 halves. What's the new power going to be? 7 halves. And then in front I just put the reciprocal. Right? And do you see why? Real quick. Is there a number in front of this? Is there a number in front of this right here? There's a 1, yes? So whatever number is here, that better kill it when it comes down. And it does. That's why I multiply by the reciprocal. So that it kills the power that's coming down. Keep going. You do the same thing again. So that's why this is so beautiful, is the same rule applies to each piece. The new power here is go up 1. 3 plus 2 over 2, right? So when you integrate fractional powers, you just add the top and bottom, put it over the bottom. Done. 3 plus 2, 5, so it'll be 5 halves. There's a 4 out here already. So what's going to go in front? Because of the 5 halves? It has to be what in front? Same way we did this. There's a 5 halves, so it better have a 2 fifths. And then finally, 4 times, this will be u, I don't need all that. 4 times. The new power here will be 3 halves. So in front of it, it's got to be, here. All right, somebody cool that? The new power is 3 halves. So what's got to be in front? So here, the new power was 7 halves. There was 2 sevens in the front. Right here was 5 halves, 2 fifths in the front. Here is 3 halves. What goes in front? 2 thirds. All right. And now you just clean it up, right? You can bring the 127s in. You can multiply this stuff. Bring the 127s in. You can multiply this stuff. Is that cool? Sort of. Again, all right. Is this clean? No. Is it hard? No. The beautiful thing about variables to a constant power, they have the single rule, right? Except for one thing, right? How do you integrate this? Yeah, that's what it is. How do you integrate it? It can't be this, right? That would be that rule. This is the one time the rule doesn't work. Where did 1 over x come from? What did I take a derivative of? ln. Okay, so that's the one thing that doesn't follow that rule. Because it can't. It would be infinite. Nobody gets to do that. Okay. All right. Trying to help you. I know it's like I beat you up a little bit. So we're going to get into some new stuff. And again, I mean, if you look at all of this at once, doesn't that look, holy shit? Of course it does. But if you think about each step, all I did here was FOIL. All I did here was distribute. Here I did each thing one at a time. Bam, right? So if you look at it after it's been written, it's like, oh my God, but piece by piece. Okay. So I feel bad because I couldn't find my visual aid. So I have still a visual aid, but it's going to be digital. I'm going to go to in a minute. So we're getting into 6.2. 6.2 and 6.3 are sort of a package deal. But thankfully we split them up because they're kind of both kind of big ideas. And what we're trying to do is you're trying to figure out, okay, if I have a shape, yeah, let me just do this. Right? So I have a shape. And I rotate that. So let's say I rotate it around the x-axis. Can you guys all see what that would end up looking like? Wouldn't that look like a football, sort of? Can you guys see that in your mind's eye? So if I rotate this, so like this would go there, so it'd be like that, but it would be 3D, yes? Which I can't do too well. Poor little thing. Let's try. Trying, little dude. There we go. It's a little bit better. So it's looking at you. So can you see that? So unfortunately, so I have this thing, and I open it up, and it becomes this ball. Right? Okay. So the question is, using what we know, can we find the volume of that? And the first thing you should say is, wait a minute, integrals tell me, what do integrals tell me, geometrically? Area. And what I just said was, can we use what we know now to find the volume of that? Well, all right. So, what's another thing that integrals do well? In fact, what does this symbol mean? So let's kind of go further down than just area. Let's go a little bit further into what it does. Anybody remember that what symbol? Why does it look like some letter that's been stretched? What letter does it look like it's been stretched? S. Why? Why does it look like a stretched S? Because old times math people did a lot of drugs. So that's how all the letters look. No. Well, maybe. Yes, sometimes. Why does it look like an elongated S? Why did we choose the letter S? Where did it come from? Yes, good. All right. This came from blah, 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 right? Infinite sum. So the math people, when they were momentarily lucid, they said, ooh, sum, starts with the letter S. Let's use a long S, yeah. Right? It could have been anything. That's basically, that's the exact moment. I mean, just everybody with me? I mean, one level of mathematics is always, why did they use the SIN? Why did they use LOG? Why did they use this shit? Because they had to use something, that's why. And they just picked something. I mean, so sometimes what they picked was like the S thing. It's related to sum. Starts with the letter S. Hey, it makes sense, right? But other symbols don't immediately make sense if you really think about it. What the shit? Doesn't it look like a divided by symbol? Is that the, do you understand what I'm saying? Maybe. So on one level, it's kind of like the symbols themselves had to be thought of. So we just have to interpret the symbol to know what to do, right? Okay. So I've drawn, what's the shape I just drew right here? You got to think of the fact that it's 3D, right? So if I had the shape and I rotated it, any point on this curve, what shape will it make if I rotate it?
Circle.
A circle. It's a freaking circle, right? Now, of course, we're looking dead on, and I'm trying to show you a little bit sideways, so it doesn't look like a circle, but you can imagine if it goes into the board and out, it's a circle, yes? Isn't this specifically at this point? That would make this, so this point would make that circle, yes? What if I used a different point? What would be true about its circle? Any different point besides that one? What's true about the circle it makes, Jeff?
It's gonna be smaller.
Smaller! I'll calm down. So if I want so here's the beautiful thing. Integral does mean area. But on a more technical level, it adds things up. So if I go from here to here, and every time I take a step, Jeff? Every time I take a step, I got another little circle. Another step, another circle. How would I end up getting the entire volume? What would I do with all these circles I created? I would just, what do you think?
I know.
add them up. Yes? Maybe. So if I had a stack of, there's these things, they were called records. They were like big CDs. There were these things called CDs. There are these circle things, right? So if I had a stack of records, if I took the area of each record and I added them up, that would be sort of like the volume, especially if they were thin. Okay, give me a break. So what's the one little thing that doesn't quite match up with that? I took the area of each record and added them all up. I'm actually ignoring how thick each one is, yes? So here's the full picture. I don't really just make a circle, I make a disc. I make a disc, yes? So if I took this out and I put it right here and I turn it and I face it to us, I see this. I see a circle. But if I look from the edge, it's a disc. I really want to make it. It's very cool, just the circle. If I chop this anywhere, I got a circle. Bam. Yes? But as I do this, it's really a disc, because how wide would this be? This would be dx wide. So as I go dx, so instead of just a rectangle where it's dx wide, yes? Instead of just a rectangle where it's dx wide, I now have this disc that's dx wide. And if I add up all these discs, if I keep going through and I get a bunch of discs, pretend like they actually physically make sense. If I add up all the areas, and the volume is really all the areas times their width, if I add them all up, I get the total volume. Okay, so somebody help me out. We kind of use both of these pictures. So this is straight on, and this is from the side, right? What is the area of this? Pi squared. That's incredible. What is the volume? Believe it or not, that is a cylinder. That is a really flat, broad cylinder, right? Isn't a cylinder this? Couldn't you make the circle big and make the height small? Isn't that what that is? So the volume of this is easy as shit. It's the area of the face times the height, in this case it's the thickness, right? So this volume is pi r squared dx. Let me call this dV. It's a volume element. So then, if I add up all of these, isn't that what that means? If I add up all of these, let me see if you guys can do this. What's the integral dV? V, right? Integral dx is x. And don't worry about the plus c because it's going to be on this side. So V, and this is going to go from something to something, right? What would the limits here be? What would I have to tell you to figure out what the limits are? What variable is it that I'm following? What axis am I on? X-axis. So I'd have to tell you this and this, and that would be a to b. So every time I take a step, I get another little disc. I add it. Take another step, I get another little disc. Add it. All the way from A to B. That's what I mean by it scans from A to B. I love you guys. Some of you guys look like, oh my God, what have I done to myself? But this isn't that crazy. So integral basically means area, but we do have a slightly more technical definition. It is an infinite limit of sums of things. So if I have a bunch of volumes and I add them all up, I'm going to get the total volume. Right? That's what integrals do, is adds up a bunch of shit. So what is this? So somebody help me out. Is the radius the same all the way through? No. So, this is terrible. I'd have to tell you, in fact, anywhere I go, anywhere from A to B, anywhere I go, what will the radius be? What does the radius depend on? Why did I stop where I did? Go ahead, sorry.
Height.
True, radius is height. But what is it? Well, if this is f of x, what will this radius be? F of x, at that point, right? So if I'm at some point C in here, the radius will be f of c. Just like when we were doing Riemann sums. And I said the sum of the height times the width. What was the height? The height was just the function, right? Depending on which endpoint we used. Here, the radius is the function, isn't that and then the function is what I'm rotating. So isn't that distance from here to the function, isn't that going to stay constant? Isn't that what the freak a radius is? Is the constant distance out to the edge? Okay, so then this becomes an integral from a to b, pi f of x squared dx. Now, of course, it's going to get a little more interesting in some places, but that's fundamentally what this is. So let me show you, now that I've tried, now let me show you better animations real quick. This is going to take a while. Cheers. This is going to be nifty. Yeah. Okay. So I kind of graphed a little bit different of a function. So it's sort of related to the one I got up there. Couldn't I have, if I wanted to, made the function, this function up here, couldn't I have put it so that the high point was at the origin? I would just shift it over, right? Okay. So that's what I'm going to use up here. Alright, I'm going to let you look at that. That looks like a taco and a toaster or something. I don't know what that is. So taco and taco. So you see how it's basically the same. It's less footballish, let's say. It's a better half circle, yes? This is interesting though, right? So what I've done, all right, let me say this right now. I'm going to say this several times. You do not need to ever draw 3D anything to do this work. But the idea does create a 3D object, right? Okay. So if you suck at drawing, like me, thankfully you don't have to be able to draw 3D really well, right? But let's take a look at what the 3D actually is. So there's the shape. It's the same thing as that. I just moved it over. So it's right in the middle. So let's watch it. Now here's what's really cool. This is what we can't do with our XY plane normally. We normally can't look at it from the side. You see how I have a third axis here? So now it's 3D. 2D is XY, so 3D is XYZ. So it's like coming out of the board. So it's like what I'm trying to do here, but I can actually come out of the board and into the board. So watch, it's cool. You see the shape is just being repeated as I rotate it? There's Pac-Man. There. So it made a nice sphere, yes? That's cool. Yeah. Rotation. Halfway. But that's what's happening, and that's basically the actual physical thing I had was you just open it and it kind of does that. That is what this is doing. Okay. Do you see the form the equation I've got up there? I don't know, you probably can't see it quite. I'm going to put it up on the board. We're going to actually do this problem right now. Square root of 1 minus x squared. Does anybody know what that's the actual equation of? I gave it away a minute ago. The top half of a circle, right? So let me write it up on the board. Okay. So that was a quick thing. The nice thing with this thing I'm doing up there is you could put different functions in. So if somebody reminds me, I can actually share the link to this with you, and you can actually put functions you're working with into this. Okay. So let's see. The function I'm working with is the square root of 1 minus x squared. And if you square it, add x squared over, you get x squared plus y squared equals 1. Unit circle, right? And the graph of this is that. Really gross, but again, your sketches don't have to be perfect. And I'm rotating this around what axis? The x-axis. So when I do discs, I locate the discs along the axis I'm rotating around. Does that make sense? Because if I rotate around the x-axis, I'm making circles this way. So I want to move on the x-axis to catch all the circles. This is huge. Because 6.2's idea is dx, sometimes dy sometimes, and 6.3's is the reverse. So it's really important for you to know when is which what. Right? So for discs, it's really cool. Whatever the shit you're rotating around, if you want to use discs, is the integral of that, d that. So if I rotate around the y-axis, it would be integral dy. Is that cool by itself? Sort of? You're all like, I have no idea. Okay. Now the idea here was this. So this is the idea. Sometimes that's dy, it just depends. But here's dx. Why again is this dx? I'm rotating around the x-axis. That's it. What are these going to be? So again, everything in this problem, the most important step in these problems is this step, determining what this is. Now everything comes off of that. So what is this variable doing to catch this whole region? Going from what to what? -1 to 1. That's the whole region, yes? So once you write this down, that focuses your attention. Everything is about x. The function inside has to be a function of x. These have to be what x is doing. If you put dy there, all that changes. Function inside, you've got to be a function of y. These have to be what y is doing. So what is x doing? Going from -1 to 1. Now there is something you could do to make this quicker, but I'm not going to talk about it yet. Some of you guys might already know. Maybe? All right. So what has to go inside? Pi. Can't I just put that out here? Because what is pi? Not the value, but what is it physically? Geometrically, mathematically, what is pi? Is it a variable? No, it's a constant. So it can come out, yes? What's my r going to be? So if I pick an arbitrary place, how long is the radius? That. Now right now that looks gross, yes? But what saves me is what am I supposed to do to my r? Square. Shit, yes. So all we are doing, pi r squared and adding them up. That's all this is doing. And what is r is the distance. Now let me be more general. What's the axis of revolution up here? What's the axis of revolution? X-axis. What's another name for the x-axis? Fred. No. What's another name for the x-axis? Anybody know? What's a mathematical name for it? Y equals 0. Think about it. Where's y 0? The x-axis. So if you see in the homework, revolve around y equals 0, they're saying x-axis. You guys with me? So what's the y-axis? X equals 0. Crazy shit. Right? Crazy shit. So pi function, basically, right? It's the distance between the axis and the function I'm rotating. In this case, that's really easy. Just whatever the function is, because it's 0 to the function. All right, how do I do this? Now, so here's the thing. If I graph this in the calculator, is it going to look 3D? If I graph this function in the calculator, is it going to look 3D? No. So what if you look at this integral, it itself is not three-dimensional. But what I've done is I've taken the volume of the thing and I've smushed it into an area of this thing, so then the integral can do it. So there's two levels to this, and I don't know how much to explain right now because I'm going to freak you guys out, but this is nothing you have to kind of know to do. This is adding up a bunch of areas. This looks like the integral of a function, which is area, right? So it's like, this isn't volume, this is area, but I've just taken the volume of what it would be and I smushed it. So what's the first thing I can do with this, obviously?
Take out the square root.
Yeah, the square and the square root dot. And then that's it. Right? How do I integrate that? X minus, yeah. And then evaluate from, anyone. So again, we got kind of like two levels here. This shit, and then once I get this set up, now it should be easy, or relatively easy. So then I get pi times 1 minus 1/3 minus -1 plus 1/3. Is that cool? So I get 1 plus 1, 2 minus 2/3. What's 2 minus 2/3? Yeah, so you get 6/3 minus 2 and 4/3. Let me real quick. Who remembers the volume formula for a sphere? Anybody? Anybody remember the volume formula for a sphere? You're all like, I don't remember my freaking first name, dude. We started off 4/3 pi r cubed. What's the radius of the sphere we create? If I rotate this around and make a sphere, what's the radius of it? Is that 1? Isn't it 1? Yes? So I mean the radius of the sphere, not the radius of the little cross sections. Yes, the radius of the sphere is 1. So if I put a 1 in here, don't I get 4/3 pi, what we freaking got? Of course we get that, because that's what the volume is. So why don't I just do this then? Because that's not always going to be a sphere at the end. Maybe the function's going to look like that. When you rotate, it's going to be all like...
So why is it 1 when it's a whole sphere?
So, isn't this radius 1?
Yeah.
So if I rotate it, isn't that the radius of the sphere? Right? How far? So the radius of the sphere is going to be from the center to the outside of it. So even if it's coming out here, it's going to be 1. Okay, leave it. So remember when we first did integration? Didn't they give you some problems that they said integrate using geometry? Okay, so here we can find the volume using geometry if it's a shape that I know the formula for. Will I know the formula for every shape? No, because if I rotate this thing around the x-axis, what shape is the result? It looks like an asteroid or something. I don't know, right? That's not a sphere, so I need calculus then. All right, so let's do this. Yeah, I got a little bit, tiny little bit of time. Let's do another one, fresh. From the beginning. So let's do, let's say, y equals x squared in the first quadrant, rotated around the x-axis. Pay attention to this kind of thing in the book, right? So when you go to graph a little sketch of this, you only have to do the first quadrant, right? Why draw anything else? You guys with me? Now, it could also say, well, maybe that later. I'll show you. So can you take a second and graph that for me? Of course you can. That's all you gotta do. Just capture the general shape of it. I should give you another wall, any quadrant one. Let's say from x equals 0 to x equals 1. Is that cool? Do that for you at least. Otherwise, it would be infinite. So can somebody give me an idea? I could have done something different. Okay. If I rotate this around, so always do this for yourself too, right? So you have a quick visual to make sure what the shit am I doing. Because the rotation axis is stupid important. So if I want to use disks for this problem, this is going to have to be integral d what? dx, because the rotation axis is x. Section 6.3 is going to be a different method that I can use if disks don't work. And it's going to be kind of the opposite. It would be dy. Let's make that look like a left there. When this is dx. Okay, we're going to get there. So let's pick out what we need to know here, right? And again, I'm going to do this without any 3D, just so you know you don't have to. So what am I going from to? I can immediately tell. And I basically gave it away from the beginning, but what am I going from to? 0 to 1. Okay. Pick an arbitrary place in there, right? From 0 to 1. Just pick one. I don't care. Here. When I do rotate, can't I draw the radius in? I don't need 3D, right? What would the radius, wouldn't it be just this? Isn't that the radius? Because if I took this point and I rotate it, isn't that going to be the radius of the circle? I really want you guys with me. Because again, some of you guys are awesome drawers. Go ahead and make 3D beautiful. That's fantastic. The rest of us will be jealous. But the rest of us don't need to draw 3D. That's fun. Thank God. All right, now let's identify what we need. We know it's disks. In fact, it has to be disks. That's the only thing we talked about. So, but later it's going to be a determination. Is it going to be disks or is it going to be the other thing? It's disks. So what do I need? We got this already. We got this figured out. So now I just need r squared, and we got that figured out. What is r? X squared. And that's how far it goes. Is it goes up to x squared. Now be careful. What do I have to do with that? I have to square it. So don't say to yourself, "Oh, it's already." No, you got to square whatever shit it is. Can you guys see what kind of shape this would take on? Anybody? What kind of shape would that be? A really strange kind of curved side cone, right? Kind of like a weird. It would need a stem, like a little base if I wanted to make a glass out of it. Otherwise, or maybe it's the top. If I put a little thing on the top, I can just spin it and make sure what level of dream I'm in. No exception for okay. All right. So now this is going to be relatively easy. What's the integral of x to the 4th?
4. Wait. 1.
What's the new power?
5th.
There. New power first.
That would be 1/5.
There you go. So whenever you integrate stuff like this, new power first because it tells you what that's going to be. And I want to go from 0 to 1. Here's a little trick. If you have a parenthesis, you don't have to put the bar. You just put that in parentheses. So yeah, so 0 would be 0, so put a 1 in, I get 1/5. That would be the volume. Kind of crazy. Now, let me see, I'm going to try to push it. One last thing. I'm going to do something based on what we just did. So what's important here? What is the most important step on this? After you graph the region they're talking about, this stupid important. Just take a second and say, okay, what am I rotating? What's it going to be? dx, dy. So let's do one that's dy. I just gave it away, but I don't care. I kind of know that's what we're going to do. It's the last thing we're going to do, by the way, for today. Don't get too excited. So I want the same thing. But I want to rotate it on the y-axis. Actually, let me do one little thing. This is gonna, well, let's see. Well, should I try this? That might be too much. Let's do, y equals 0 to y equals 4. One little thing that would have been a little too much in here. So what is this going to look like? Well, it's still going to be y equals x squared. Right? But where is y equal 1? What does that look like? That wall, y equals 1. I kind of just gave it away.
Yeah, why?
Where was x equals 1 in here? Remember it was from x equals 0, x equals 1? Where's x equals 1? I drew it. What's x equals 1 look like?
It's be a straight line.
Not like this though, right? Yeah, there it is. See, there's x equals 1. Every point on there is an x equal 1. So what's y equal 1 look like? There you go. Every point on there is going to be y equal. There you go. There's one wall. There's another wall. There's another wall. It should be y equal, but that's fine. All right. That works for me. So it's the same function. I've just got a different kind of half of it, a different part of it, right? And I'm going to rotate this around the y-axis. So very first thing you do after you graph the region they're talking about, the very first thing you do is integral d what? D1. Okay, we did that before we even did this, but again, it's because I'm rotating around the y-axis. So put your little rotation symbol. So what, now this is a little bit, I could have made a little bit better problem, that's all right. What do these limits have to be in terms of?
Y.
But what's y doing?
0 to 1.
Okay, so we're kind of easy, that's kind of easy here. But 0 to 1, but those are what y is doing. I could put my pi on the outside because I know this is the disk method. But can I put that in here?
No.
Of course not. So my disks, I locate them along the y-axis now, right? I'm going to rotate this thing around. Well, that's great. Okay. You can tell it's like a drawing. Okay. So this has to be a function. So I gave it to you as y equals x squared, but it's got to be a function of y, right? How do you when you solve that for x? What do you get?
There's Y.
And how do I know it's not plus or minus? Because this is the positive part. So again, what told me I had to take what they gave me and solve it for the other letter was because I need a function of y in here, right? So that's why this is the first thing. It tells you what these are. It tells you what goes in here. So now I put square root of y in there, and thankfully, what do I do to it? Square it. Yeah, it's the same idea. Right? It's disks. They always work the same way. So if I pick this is going to be the function, right? Man. That's the radius. So I get pi 0 to 1 y. I get pi 1/2 y squared from 0 to 1. So I get, when I put a 1 in, I get 1/2. I get pi over 2. So why does it make sense? I don't know if you guys can see this. You see how this kind of goes out? So when I rotate it, I get a bowl. Yes, can you guys see that? It's going to be a bowl. And do you see how this goes out, so I get more volume. Do you see how this goes in like this? So when I rotate it, I'm losing. So that's why it makes sense. That's pi fifth, and this is pi halves. This is going to be bigger because it goes out more. I pick up more volume when I rotate it. Okay, that was a lot. All right, so next time we'll get deeper into disks. We might do a little bit of a preview of the next method. And it's easier once I get both of them out there, because then I can talk about contrasting when to tell which one to do, right? And eventually I'll give you this. I think it's still a little too early. It's my most colorful handout that I've ever made in my entire career, which is not very colorful. All right, guys. I'll see you Wednesday, hopefully. Can you guys at least come back? Let's see if anybody else comes. No? Axel says that's it, man. I'm done. All right.